some of the parts. So we'll cover one by one in linear algebra. So what is linear algebra? Then vector spaces and subspaces, what we mean by scalars, vectors, matrices, vectors and matrix calculation will go after that, and some of the determinant properties and how we are going to solve simultaneous equation, what actually from I think 10th class. But now we'll take it as geometrical application, and we'll see these simultaneous equations are very much useful in different applications also. And then we'll go after some basic applications related to chemistry, cryptography, linear programming, even networking is there. Okay, Fibonacci
Thakran sir,
numbers, geometrical. Sir,
Thakran sir, kindly make it in the slideshow mode.
okay, yes, sir. Is it going on now, sir?
Yes, it's going on. Yes, make it on slideshow presentation.
Okay, I think then in that case, just
Uh,
a moment.
on the left, on the right side of your slide, you can see a logo or
Yes, yes. So I think I need to change this. Just a moment, sir. I'll stop presenting and I'll again take it back. So I think now it's okay, sir. Hello.
yes, now it's perfect. Perfect.
Okay, sir. Okay.
Yeah. Yes, please.
So these are the topics which we are going to cover in our linear algebra. Okay. So first of all, comes in the mind what we mean by linear algebra actually. So it is nothing but it's a mathematics, a branch of mathematics which concerns about the vector spaces and the mappings between the spaces. So the first question is, if it is a branch of mathematics concerning with vector spaces and the linear mappings between spaces, then what is vector space? Okay, and how we are going to basic part of it, or we can say that it includes the study of lines and planes, more commonly. So first of all, moving on towards the vector space, the first thing is what is vector? Now we all know that vector means it has magnitude and direction, but that is a physics vector. And if we talk about a mathematics, in mathematics, so column of numbers. Okay, we have all gone through the matrices. So if we consider a matrix and each column matrix represents a vector. So whenever we represent a column matrix only, for example, this matrix I have taken x1, x2, x3, it's a 3 by 1 matrix. It also represents a vector of three-dimensional space. Okay, where x1, x2, x3 are nothing but a coordinate system in a in that three-dimensional space. So the space means this is just a coordinate of that whole, you can say that whole set. Okay, so this represents a vector. So vectors are nothing but it has it can be more than three components. Okay, but if it has less than three components, so most commonly what we have seen is that a vector is containing n elements, a vector is containing 5 elements, 6 elements. But if we reduce the components of a vector, then how we can visualize it? It's just like this. So if I consider it two-dimensional, and let us suppose V is defined as a vector, then its component is be taken on x-axis and y-axis with v1 component and v2 component. So that means the point, the value at this point will be our coordinate v1 comma v2, or sometimes we refer it as in the form of column matrix v1 v2, that is a 3 by 2 2 by 1 matrix. Similarly, it is a three-dimensional vector. So it has component v1, v2 and v3, to which we have just right now taken this part. Over here. Okay. I think now it's okay. I'll click here. Note from my side. I think again. Okay. Okay. Okay, I think there is some issue that my screen was fading. Some of the participants were not able to see this PPT. So I'll start again with vectors. So vector is nothing but column of numbers. And when we talk about vectors, the visualization which we can see is only in two-dimensional and three-dimensional. So right now I have talked about the, if I consider a vector that is a column matrix having two rows and one, okay, 2 by 1 order. So the values of that matrix refers to coordinate v1 and v2. Similarly, if I consider a matrix of three components, that is having order 3 by 1, then in that case, on x-axis it is v1 component, y-axis v2 component, and on z-axis it will be v3 component. So in general, this is my vector v, which can be defined in this way: x1, x2, x3, or we can consider v1, v2, v3, or we can consider any format. Okay. So these are the things how we define a vector in the form of matrix. So this is the mathematical representation of a vector. Now, so once we have understood how we can represent a vector in mathematics, then what we mean by a vector space. So if we collect all these vectors and we define only, we define that whenever we add two of the vectors, then the result is again will be in the same set. So it's just simple definition. It simply says that if a set of objects B is a vector space, then the objects are vector space, and these vector space holds addition and scalar multiplication. So that means whenever we take any two vectors, their addition, and if I consider any alpha to be a scalar, then alpha multiplied with that vector u or vector v, that is again in the same set. And if it holds these following axioms: associative, It should contain a zero vector. It should contain the inverse of the given vector also. Okay. Now this is called Euclidean space or Euclidean property. So together a set with these properties. Now this zero vector is very unique, and we'll see later on. And Rn is a general vector space where each element contains n rows or n components. So if I consider Rn to be a vector set, okay, then the basic idea, let us consider the value of n equals to 2. So the moment I take n equals to 2, it forms the R2 space. And this set R2 will hold such type of elements, right? A coordinate system containing x1, x2, or a 2 by 1 matrix of such forms. Or simply, we can say that it is a coordinate system. And this is nothing but my R2 space because it holds all the properties which we have discussed right now. Now, how the addition of these vectors will be taken place? Now, this is the best example. Instead of taking the elements, two vectors. Let's say A is a vector a1, a2, and B is a vector b1, b2. Then by the single sum will be now in this vector a1, a2 is nothing but a1 is the component on x-axis, a2 is component on y-axis. Similarly, vector b1, b2 is b1 is component on x1 and b2 is component on y. Let us take the addition of these two, a1 and b1, a2 and b2 be defined by, if you take the sum, yes, it will move further, a1 plus b1 and a2 plus b2. And the intersection of these 2 points forms the coordinate system a1 plus b1, a2 plus b2. Now this component, this coordinate in xy, or we can say that in R2 space, let's say R2 space, this is the sum of the two vectors. Okay. And further, this part can be written like this. The corresponding elements gets added of the matrices. So this is the geometrical interpretation of the vector addition. Now, the vector products, this part is very interesting. Uh, let us take two vectors of order 3 by 1. Okay, so here I have considered a vector x1, x2, x3, a vector y, which is y1, y2, and y3. Now, there are two type of products which is defined. One is called inner product and one is called outer product. Now, what is inner product? If I take the transform of the vector x and if I multiply with vector y, then the result based on the order matrix multiplication, x transpose becomes order 1 by 3 and y vector is of order 3 by 1. So definitely the result will be of order 1 by 1. And when I say the result is 1 by 1, that means it is a matrix of order 1 that represents a real number. And the moment we define a matrix of just a single number, then it forms a scalar. So the inner product always results in the form of a scalar. Whereas the outer product, so for outer product, we take the transform of y, transpose. So if I take X, Y transpose, the product of these two, then we know how the matrix multiplication is defined, right? So a matrix of order 3 by 1 multiplied with a matrix of order 1 by 3, so the result will be a matrix of order 3 by 3. So outer product always results in the form of a matrix. And the result is, as you can see, it is x1, y1, the diagonals x2, y2, and x3, y3. So the vector product is very simple. We just have to take care of that. See, what type of result we want? We want a scalar or we want a matrix. Okay, and based on that, either we use inner product or we can use outer product. There are some special vectors in the vector space. One is zero vector, and this zero vector can be of any dimension, or it can be of any size. So we can represent the basic, because zero is the identity matrix, or zero vector is the identity vector of any vector given in the vector space. So 0 plus v is always v. Okay. And if we take the multiplication of it, then the result is always the zero vector. Based on these two property, this zero vector is also important, and these are the standard vectors. So we have seen the identity matrix, right? Now, if we pick each column of identity matrix of order n, then each column represents these standard vectors. We represent it by the vector e1, whose first component is 1 and the rest of the component is 0. Standard vector e2, first component is 0, second component is 1, and rest of all the component is 0. And similarly, so depending on the size, we can use the standard vectors. Now, so vector space, when we talk about when we say vector space, so it is a set, and that set contains some vectors which satisfies the basic property of addition closure and scalar multiplication closure, along with the basic axioms which is called as Euclidean space. Okay, subspace is a part. Okay, when we say subspace, it is a subset. So space and subspace, we are talking about only set. So subspace, it is a set, a vector set, which is a subset of the whole space. Okay, or a vector space. It should satisfy just three properties. The first thing is the zero vector should belong to the subspace. And whenever, if we consider two vectors, whenever we consider two vectors from this subset, then the addition is again belongs to the set V. That means it is closed under vector addition. And third one is, if I consider a vector u and C is a scalar, then Cu is again in the set V. That means if I consider a subset of a vector space, then it should have these three statements. The subset. That subset should contain a zero vector. That subset should satisfy closed addition. The addition should be closed, and the subset is also closed for scalar multiplication. And in that case, then the result that subset itself becomes a subspace. Okay, so a smaller portion of the vector space which holds these properties. That is what we mean by a subspace. Now, once we come to know that subspace is nothing but it is a subset of a bigger set, subset of a bigger set, then definitely it will have some, we can consider subspace of some finite numbers also. So finite elements, finite vectors. So if I consider these finite vectors, let's say a vector set u1 to uk. Let's see this property. So we are going step by step. Okay. So whenever we consider a vector set having a finite elements or finite vectors, then there exists a vector v which can be represented in this form: c1, u1, c2, u2, and the sum of all these vectors along with the scalars. So the number of vectors defines the number of scalars c1, c2, and ck. Okay, and this is called the linear combination. This is what we call it as linear combination. Okay, the combination of scalars and vectors. And this is nothing but the property which we have seen in vector space as well as in subspace, that is C into U. U is a vector, C is a scalar. So when we are having more than one vector and more than one scalar, then we can form it's a combination. Now this linear combination, if it represents a vector V, if it represents a vector V, then it is also known as the span. Okay, so the span is basically based on the linear combination. Okay, one, 1, 3, and 1 minus 1. Right? And if I consider the coefficients minus 3, 4, and 1, so what will be the result of this linear combination? It's very simple. Right? Let us, I'll take this part to the notepad. So, right. So this is my vector set, and these I have considered some scalars. So definitely, if I take the linear combination of these two, the scalars and vectors, so I will have minus 3, 1, 1, plus 4 times 1, 3, plus 1 times 1 and minus 1. Definitely, based on the addition property, the results would come out to be a matrix of order 2 by 1 again. Right? So what we have considered is a 2 by 1 matrix, a 2 by 1 matrix, a 2 by 1 matrix. And when we have taken the linear combination of these, the result is again a 2 by 1 matrix. Now this is what we call it as that these vectors, these vectors can generate any kind of vector. We need to choose what will be our scalars. If we change our scalar, the result will be different. Okay, so the result is simply a 2 by 1 matrix or 2 by 1 vector. Right? Now, this is the best example which I have taken. Suppose U1 is my image which represents a vector. Definitely it's a matrix. U to the image of stars. Right? Then, if I consider consider 1 to be the scalar for u1 and 0.5 to be the scalar of u2 vector, then the result would be something like this. As you can see, the intensity of the stars which I have taken is 0.5, and for u1 it is 1. Right? Now the linear combination is again a matrix which is combination of u1 and u2. Now why I'm saying it is a matrix? Because image, this is an application based part. In image processing, when we say image processing, these pictures are represented in the form of pixels, which later out comes to be a matrix of a larger number n cross n. So see, linear combination is okay, mixing of we are taking. Now, if I change this intensity to 1, then see the result. Okay, so this is the beautification of the linear combination. And let's say if I consider a third vector, u1 is the vector of picture of a girl, u2 is the picture of stars, and say u3 is a vector representing a picture of lightning. Then scalar for u1 is 1, scalar for u2 is 0.5, scalar for u3 is 1. So I have the scalar 0.5 which I have taken, right? Just right now we have discussed the intensity of the picture. The result is fascinating. The combination of all the vectors in one picture. Now this is what we call it as a linear combination. It is, they are just numbers, scalars and vectors. But when we apply in the real life problems, okay, then it is nothing but uh, we can say mixing of the two pictures or combining audio and video recording also, right? So they are also nothing but the linear combination only, the part of the linear combination. And further, how we can relate this linear combination with the system of linear equations. Suppose I consider a system of two equations. Say 3x1 plus 6x2 equals to 3, 2x1 plus 4x2 equals to 4. We want to find out whether this system will have a solution or not. Okay, so what we'll do is we'll bifurcate or we'll split them in the form of matrix, that is Ax equals to B, where A is your constant matrix, X is the variable matrix, and B is the constant matrix. Now the question is whether this system will have a solution or not. Till now we have seen just by checking for this matrix A, right? We check the matrix A that whether it is determinant is 0 or not. If its determinant is 0, then based on the rank, okay, or the condition, checking the consistency of the system of equation, we'll check the rank. But if I say there is no need of that for lower system of equation, we just need to check, is this matrix B can be defined in the form of a linear combination of columns of this matrix A? So this is my set of vectors 3, 2, 6, 4, and this is my vector B. The question rises, if I can represent a linear combination of these two vectors as 3, 4. Right? That means if I have C1 and C2 two scalars, we need to choose C1 in such a way that this product plus this product should be equals to 3, 4. Right? If we can get C1 and C2 in such a way that the value will be 3 and 4, then definitely we can say that yes, it will have a solution. But if it is not, you cannot find such C1 and C2 which are real numbers that it will represent. The linear combination represents the vector 3, 4. Then it will not have a solution. Now, right? So we have a vector set 3, 2, and 6, 4. Right? We want to check whether this solution or not. So right now, what we have seen is we need to check this linear combination and we need to find what is my C1 and what is my C2. So the basic thing is when we say a linear combination of these two vectors 3, 2, and 6, 4, it is a two-dimensional space. These vectors are lying in two-dimensional space. So this is my x-axis, this is my y-axis. What I need to check, the vector 3, 2, vector 6, 4, right? They are lying in the same line, right? They are lying in the same line. Now, does this vector 3, 4 lies in the same line or not? So the linear combination is always on the allotted line. When I say linear combination, it is always on this dotted line. Now see, this vector 3, 4 is not on this dotted line. So yes, I can say that it does not have a solution. It can never have a solution. And we can check based on consistency also. Right? The rank is 1 of this matrix A. What we say? Matrix A is having rank 1. Whereas if we take the augmented matrix AB, which is the combination of A matrix and B matrix, its rank you will always found to be 2. And that is what we mean by the rank 2. That the linear combination are lying on the same dotted line, but the vector which is on the right hand side of the constant matrix which we have taken, it is not part of that linear combination. So it definitely will not have a solution. So this is the best example of the linear combination how we can apply in system of linear equations. And if this linear combination, wait, if this linear combination is set not just any vector, but we know that a vector space contains a zero vector also. So if I state that this linear combination is fixed to a value 0, then this linear combination would let us out whether the vectors are linearly dependent or independent. Okay. And the condition is very simple. We need to check just scalars. So if a1 to an are our vectors and x1 to xn are scalars, and still the linear combination is my 0 vector and the scalars are not 0, at least one of the scalar is not 0, then we say that yes, it is a dependent vector. These vectors are dependent. So I can represent a vector a1 in the form of the rest of the vectors. Or I can represent vector a2 as combination of A1, A3 and rest of the vectors. That means my vector A1 is depending on the rest of the vectors. Vector A2 is depending on vector A1, A3 and An. So this is called the dependency, where the scalars won't be zero. But the moment I say all my scalars are zero, what we are saying, all my scalars are zero, right? Then these vectors become linearly independent. Now, what we mean by linearly independent? See, it's a system of homogeneous combination. So when I say linear combination and A1, A2, An are some vectors, then this linear combination is always represents a homogeneous system of equations. It's always system of equation but homogeneous. That means it does not have any constant value, right? And when we solve this part, it will always gives a unique solution, and that unique solution leads to all the scalars zero. Let us take an example. We'll take an example of this linear combination later on. Okay. Uh, so once we come out to be that, yes, the linear combination which we have taken of some vectors is dependent or independent. We have seen vector space, its subspaces, and how some finite members of that vector space can generate the whole space. Okay, finite space. Now, this is what we mean by span. Now, span is again some set of finite elements, U1 to UK. So let us consider this is my set S. And this set is defined in such a way that it, some of the scalars say C1, C2 and Ck, it forms a linear combination. It forms a linear combination. Now this linear combination is called span of S or span S. Okay, it is denoted by span S. Now, the meaning of span S means it can generate some finite element can generate an space containing infinite vectors. Okay, infinite vector space. So I am having a vector space V where I have considered a subset S. But this subset S is containing only finite elements U1, U2 and UK. Right? The moment I say that linear combination, now we know that the basic property of vector space, subset, subspace, that it holds the property of closure for addition and closure for scalar multiplication. So what we have is we'll consider some C1, C2 and Ck some scalars that will form a linear combination with these vectors of S. Okay, and based on these scalars or based on choosing the values of C1, C2 and Ck, if I get a vector V1, vector V2, vector V3, vector V4 and so on. Not only just these vectors but each and every vector of this vector space. Then we say that yes, it spans my vector space V. That is, S is a generating set for vector V. Okay, the basic idea. Suppose if I consider S1 to be the set of only one vector, say 1 and minus 1. How we come to know that what will be the span of S? It's a straight line. the span of S is a straight line. And why I'm saying it is a straight line? Because I'll have only one scalar multiplied with one vector 1 minus 1. Okay. So whatever the value of alpha we take, if I choose alpha to be 0, it will be the origin point. If I take alpha to be the 1, it will be the vector itself. If I take alpha equals to 2, it will be double the vector 2n minus 2. And each vector, depending on the value of, it will lie on this white line. So this white line is called the vector space for this set S1. Okay. Now, instead of one vector, let us consider two vectors, 1 minus 1 and minus 2, 2. I have not considered the same. Are they same? Let's check out. 1 minus 1 is a vector in the fourth quadrant. Minus 2 and 2 is a vector in the second quadrant. Right? Now, you can see they are aligned on the same line but opposite in direction. Right? So again, there are two vectors which is spanning or which can generate this straight line, right? So yes, I can say that the span of S2 is the straight line passing through second and fourth quadrant. So based on this example, yes, it doesn't matter if it contains one vector or two vectors. In this case, my span S1 is same as that of span S2. So different number of vectors can generate the same space. Let's take one more example. Set S3 containing three vectors 1 minus 1, minus 2, 2 and minus 2, 1. So 1 minus 1 is in the fourth quadrant, minus 2, 2 is in the second quadrant, whereas 2 and 1 is in the first quadrant. The moment I got a vector which is different from these two straight lines, I can say that the linear combination of these three vectors can generate my R2 space. Now, it can generate R2 space means C1 multiplied with 1 minus 1 plus C2 multiplied with minus 2, 2 plus C3 multiplied with 2, 1. Now, it depends on what is your C1, C2, C3. Each time you will get a vector of this space R2. Now, I have considered one more example, a set of four vectors. These three vectors already we have taken. Now, this is my fourth vector, minus 1, 3. So, one vector is in the first quadrant, two vectors are in the second quadrant, and one vector is in the fourth quadrant. So, definitely, when a vector is defined in such a way, then this also can generate my R2 space. Right? So, this is the basic idea of the span, that having the limited vectors, having the finite vector, if it can generate the whole space, then why to worry about the whole space? We just need finite vectors and we can have the whole space. Right? Basis. V is a non-zero subspace. Now see, we have considering a non-zero subspace of the space Rn. Then a set, or we call it as a basis B for V, is nothing but a linearly independent generation set of V. Now, linearly independent generation set of V. That means basis basis is that set which can generate the whole space as well as the set contains only non-zero vectors and these vectors are linearly independent. Let us consider E1, E2 and En is a basis for Rn. Okay. Now, it will be our choice what value you would like to take, n equals to 2 or 3 or 4 and so on. Okay. That the first basic thing, in order to make it as a basis, we need to check whether these vectors are dependent or independent. Second, these vectors should generate Rn. Now, the moment we say it should generate Rn means it should span the Rn, it should span. Or we can say that your Rn is nothing but span of this set E1, E2 and En. Okay. Now, I have taken one basic part where I have taken n equals to 2. Okay. The moment I set n equals to 2, I'll have my standard vectors to be 1, 0 and 0, 1. And it is a basis for R2. It is a basis for R2. Now, basis means it should be linearly independent. How we will check whether it is linearly independent or dependent? We don't go after solving the system of equation, forming the linear combination. Okay. Whatever the vectors are given, just check 1, 0, 0, 1 will form the matrix and check whether its determinant is 0 or non-zero. The moment I say that determinant is non-zero, it becomes linearly independent. It directly follows that it is linearly independent. My vector, I say E1 and vector E2. These two vectors are linearly independent. Okay. And it is a basis for R2. That means it generates whole space R2, x-axis, y-axis. The element or the vector say my vector v1 is 1, 1, vector v2 is 1 minus 1. Vector, another set, vector v1 is 1, 3, vector v2 is minus 3 and 1. Another set, vector v1 is 1, 1, vector v2 is 1, 2. So, can they form the basis of R2? Can they form the basis of R2? Yes, they can form the basis of R2 if we can find that the set contains linearly independent vectors. This set contains that they are linearly independent vectors in each set. And definitely they can form the basis. Okay. Now, if our matrix is not small, say directly we have been given a matrix, and based on that matrix, we have to find the basis. Okay, and what will be its dimension? So what will I check is this is my matrix, is of order 4 by 6. Now, what are the components or which vectors can be defined as linearly independent vectors such that the linear combination of those vectors can generate this 4 by 6 matrix, or it can generate the space. Okay, so what will I do is we simply, this is the column. Yeah, columns of matrix A. I'll apply row reduced Euclidean form. The moment we apply row reduced Euclidean form, easily visible that this is my E1, this is my E2, and this is my E3, the standard vectors. The second column is just the multiplicity of E1, right? Twice of E1. And rest of the columns, they have not been converted into the standard. So row reduced Euclidean form is to find the standard vectors. Once I get the standard vectors, what will I say that these standard vectors, which are representing these three pivot columns, are nothing but my span. So this set, so 1, 2, 3, my column 1, column 3, and column 4. So these three vectors is nothing but my span. So this is also finding the basis of its column space. Now, these are all the ideas about the basic part or theoretical part of what we have gone through, the vector space, subspace, what is linear combination, okay, what is span, what is basis, and we have seen how the linear combination can be included in the applications. Now, moving forward to some basic part, because all these vectors, when we combine, it forms a matrix. Now, it doesn't matter what order of the matrix it can form. Okay, it can be a rectangular display having n plus 1 matrix, or it can be a 3 by 3 matrix, or it can be 3 by 2 matrix, or it can be of Dij, ith row and jth column matrix. Okay, so this is nothing but the vectors combined together. So I'm having a vector of order 3 by 1, V1, vector of order 3 by 1, V2, vector of order 3 by 1, V3. So when we combine the vectors together, it forms a matrix. That means I have some components. Now, visualization of these components is nothing but they are the points. Okay, the place values in the arrays. Okay. Now, matrix calculation, of course, addition is commutative, associative, and the meaning of addition is adding the corresponding elements. Okay. The basic idea of adding the corresponding elements that A and B should be of same order. If they are not of the same order, then I'm sorry, we cannot add that. Okay? Okay. So if A and B matrix are of same order, then the addition is possible, and based on that addition, my addition is commutative, it is also commutative. Similarly, subtraction, on the same hand, is nothing but it is the adding of the negative matrix. So if I am having matrix A and matrix B, and I say we have to subtract these two matrices, so I will add the matrix A with with additive inverse of matrix B. Now, what we mean by additive inverse? To just multiply with the scalar minus 1. So, this is my scalar minus 1. Now, see, it's a linear combination. 1 dot A plus minus 1 dot B. This is my linear combination. So, I'm taking the linear combinations with some fixed scalars. Okay, so they gives me the result fraction. Scalar multiplication. Sorry. So scalar multiplication is a simple thing. If we multiply a scalar lambda with a matrix, then that scalar gets multiplied with each element of that matrix. Now, the moment we are saying that it multiplied with each element of the matrix. Just see the visualization. Suppose this is my vector V, which is representing the coordinate x1 and y1. Okay, so this first column is my V. So if I take the product or scalar multiplication lambda, that means I'm taking the linear combination with the vector x1, y1. That means I'm extending my vector v to lambda times. So the extension of lambda times, say that is w. So the result will be lambda x1 and lambda y1 as the column components. That's why when we say scalar multiplication in matrix, that scalar gets multiplied with each component of the matrix. Okay. So this is a basic thing, scalar multiplication. Let us consider a 2 by 2 matrix A and B. And matrix multiplication is also the interesting part. It should be valid. The result or the product of these two matrices should be valid. And validity can be checked based on the order if a matrix A is of order m cross n and matrix B of order, say, L cross K. Right? We say we want to take the product of A and B. Then this product will result out in a matrix C whose order will be m cross K. But the result is possible if and only if the value n and value L they are equal. So that is the guarantee. That gives the guarantee that yes, the product of these two matrices is possible. Right? So taking a 2 by 2 means matrix multiplication. The definition is very simple. If we understand it, sum over product of respective rows and columns. Respective rows and columns. So this is my respective row R1 whose respective column is C1. If I take the product and taking its sum, then the result is my C11 component. So respective row and column gives the respective position in the final matrix. So C11 results out in the product of R1 to C1. Okay, so this is my R1 multiplied with C1. R1 multiplied with column 1. This is row 1 multiplied with column 2, row 2 multiplied with column 1, and row 2 multiplied with column 2. So respective rows and columns, and it is nothing but sum over product. And as the matrix gets bigger, then we have the basic tools for simplifying these matrix multiplication. Say we are having MATLAB, we are having or the softwares. Okay, but if we want to if we know how we can solve it manually by taking a smaller matrix, then definitely we can define, define the programming of a larger matrix also. Okay. Matrix multiplication is not commutative. So these are the three basic ideas. Okay. Matrix distributive. Now that's a very good part. Distributive. So matrix multiplication holds these two properties, associative and distributive. But yes, it is not commutative. But under one condition, this matrix multiplication is commutative if and only if, okay, but we can say that A multiplied with B is same as that of B multiplied with A under one condition if A and B are same matrix. Basic condition of having that the product is commutative. Now, determinant. Determinant, the thing is that it says we can find the determinant of only square matrix. But what is determinant? Right? So right now we have been gone through some matrix multiplication, addition, and all these thing parts. We have seen combining the vectors forms a matrix. So the determinant is nothing but it is the representing a value. It represents a value of a given matrix. Now this is the basic idea or visualization. What we mean by actually the determinant. Okay, for 2 by 2 matrix, if A is my matrix 2 by 2, A, B, C, D, then we know that determinant is defined as AD minus BC. Okay, from the childhood we are learning this formula that the determinant is always AD minus BC. But if I consider these to be as vectors v1 and v2, okay, or you can consider vector AB and CD. It doesn't matter in which format you are taking. If you take transpose, then this will be my v1. This will remain same. It doesn't changes. The meaning of that is if this is my vector v1, which is having coordinate a comma b, and this is my vector v2 having the coordinate c comma d, then the result is a plus c and b plus d, the addition of vectors. Okay, in the starting slides we are taking the addition of vectors. So the product, we are saying AD minus BC. It is nothing but the area enclosed by this rhombus or this region. So this region, which is enclosed by these two vectors, having the result AD minus BC is nothing but is actually your determinant of the matrix A representing the vectors A, B, C, D. Okay. But this part we can visualize only up to 2-dimensional or up to 3-dimensional. Okay, if I consider 3-dimensional, then it forms a volume part, right? The examples we have taken for this determinant, we find the volume of the parallelepiped, right? Find the volume of the tetrahedron. If I consider a vector in 3-dimensional and it forms a parallelepiped, right? Then what will be the volume? So it's simple. I will consider the vector form of this parallelepiped and I'll check out its determinant. The moment I consider the determinant of this parallel pipe, which is a matrix of 3 by 3 order, right? It gives me the volume part. Similarly, for 2 by 2, it gives me the area part enclosed by these vectors. Now, what is the benefit of finding this determinant? Why we are finding this area, calculating this volume, right? In order to solve the simultaneous equations. We require this area, we require this volume. That's why we require the determinants. So if I need to solve, if you need to solve a linear equation and B is constants, right? X, A, B, and B are only three possibilities of this system. The first possibility is what happens if the value of A is 0 and what happens along with this A if B is 0 and B is not 0. So see, if A is not 0, then definitely we can write down it as B divided by A, but which is similar to that of A inverse B. The order. Why I say order? Because A is on the left hand side. Your A inverse should always remain on the left hand side, left side. Thus, it gives a single solution. But if both the values are 0, if A is also 0, then B is also 0. Having the equation equality, I can say that X can be any real number. Whatever value I take for X, my equals to 0, right? So it gives X will have infinite solution. But if P is not equals to 0, what expression do I have? Equality is 0 equals to B. So in order to have P equals to 0, because we don't know what is the value of B, right? B is a constant, B is a constant matrix, B is a constant value. If B becomes 0, then I'll have the second situation of infinite solution. But if B is not equal to 0, then it is a contradiction. It is a contradiction. That means it will not have any solution. So determinants are used to solve system of equations. Okay. Now, since we have seen the consistency part and how to solve the system of equation, let's move on to the chemical applications. Some of the applications I have collected and I'll share with you one by one. Uh, most of us are afraid of the organic chemistry, how to balance the equations. Okay, so I also do have fear of balancing the equations in organic chemistry. But once I understood this linear algebra, it's a piece of cake now. Okay, so most of the expressions are based on balancing a chemical equation and finding the volume of the substance. And behind this is a simple statement which gives how to balance. The mass is neither created nor destroyed in any chemical reaction. So, balancing of equation requires the same number of atoms on both sides. both the sides of a chemical reaction. Right? For this, I have considered one example. Let us consider a simple equation: C2H6 plus O2 gives CO2 plus H2O. Now, this equation is not balanced. It is not balanced. I need to balance what kind of hydrogen and oxygen. Two components on the left side, two component on the right side. So I'll choose four scalars: X, Y, Z, and T. And the way that this equation can be balanced, then it gives rise to, let's say, the linear combination. Okay, linear combination of X, Y, Z, T. Y multiplied with the vector O2, Z multiplied with CO2, and T multiplied with H2O. It gives a system of equations for for carbon, for hydrogen, and for oxygen. Okay. Now, since we are having four variables but three equations, so definitely this system will have infinite pair of solutions. Right? We have four variables and three equations. So based on this, my nullity is 1, and if nullity is 1, then I can choose either X or Y or Z or T to be any number, any number, right? So in this case, I have chosen, since the value of Z is depending on X, value of T, I can take it as it is also depending on X, and value of Y is also depending on X, since Y is defined in terms of Z and T, and Z and T already we have calculated from two equations. So this is my expression of Y, Z, and T. Now, since atoms cannot be a rational number, atoms cannot be a rational number. So we'll choose these coefficients x, y, z, t or scalars x, y, z, t in such a way that the value of y should be a whole number. The moment I choose 2, because it is clear, I need to choose x equals to 2. Y becomes 7, z equals to 4, and t equals to 6. And this is my balanced equation or balanced chemical equation. Okay. So all we need to understand the linear combination, system of equation, and moreover, a vector space. So only. Let's consider another example or another application of cryptography. So, cryptography is basically coding and decoding, or we can say encrypted data can be decrypted. Okay, and nowadays on internet sites, banking sector, they all use cryptography in their system, networking system actually. Okay, what we call it as, I most of you have seen it or not. The moment I say bit system, okay, or there is a unique code system, 64-bit to 56-bit and so on. So these are the type of encryption in the networking system. And cryptography is also basically sending coding messages, but all this coding part requires a decryption in such a way, that we have to provide an encoding matrix. Okay, if we know the encoded matrix, then it's inverse. Okay, so this is my encoding matrix A, and let's say this is my message prepared to a preparation to negotiation. Okay, so this is my coded message which I need to send it to another party. So what we'll do is we'll mark each letter to be from 1 to 26, and the space which is in between these letters, I'll consider it as the 27th alphabet. That will be my 27th alphabet. I'll assign it as a number 27. And I'll consider a matrix. Now, since as an example, I have taken a 3 by 3 matrix, we can consider a 2 by 2 matrix also. We can consider a 4 by 4 matrix also. Okay. So, I will write this message prepared to negotiate in the form of numbers 16, 18, 5, 16, 1, 18, 5, 27, and so on up to 5. And further, since I have considered a 3 by 3 matrix as my encoding matrix, so I'll prepare these numbers in the form of vectors. So this is my vector V1, 16, 18, 5. This is my vector V2. This is my vector V3. This is my vector V4, V5, V6. Okay. Now there is one more vector remaining, 25. So what will I do is I'll take a space, 27. And this will be my vector V7. Now, as we have seen, matrix multiplication is possible if and only if the column of matrix which we are going to multiply or which we are going to operate on a vector, it should match with it. So my vector V1 is of order 3 by 1, right? So this should match, and that's why I have considered my vectors to be of order or collection of 3 components. So when I multiply this matrix over V1, V2, V3, V4, V5, V6, V7, this is my coded message. Sorry, this is my matrix. Now I want to decrypt this part. So for description, I'll multiply with matrix A. Okay. The moment I multiply with matrix A, what I have is, let us take only one example. The matrix is -3, -3, -3, -4, -3, -3, -4, 0, 1, 1, and 4, 3, 4. Right? This is my matrix A. So the result is vector V1, V2, V3, V4, V5, V6, and V7. My first column. Now remember, you can take the product of this complete two matrices, which results out in a matrix of order again 3 by 7. It will be a 3 by 7 matrix. And further, I need to concentrate again only on the columns, the first column, because we are taking the column space. Okay. So I'll have my first column as R1 multiplied with C1. So the value is -3, 16, -3, 18, -4, 5. So I'll have some number Multiplying R2 with C1, I'll have again one number. Multiplying R3 with C1, again I'll have one more number. Now these three numbers will not match with the number 16, 18, 5, which means the first three letters 3. You cannot decode until I have read. So decoding can be done now by taking operating A inverse on this matrix. So once I operate A inverse on this matrix, I'll get back this set of vectors again, which means prepare to negotiate. So this is the application of matrix and vectors in cryptography. Okay. There are some application in elimination theory also. How we can eliminate or how we can find the solution of some polynomial equations, right? So solving a polynomial equation having degree 3 and degree 2, all we need to do is we have to compute the resultant of these two polynomials, and resultant of these two polynomials means the determinant. Okay, the moment I get, okay, depending on the determinant whether it is 0 or not, I can say that the polynomial, which theorem, this one. Okay, but the best part is geometrical application. See, geometrical application we have seen many cases from our schooling time. How to find the equation of line, how to find the equation of plane. If 2 points are given, how to find the equation of circle if center and radius is provided, right? Plane passing through a circle. All these examples we have seen. Now let us do the same thing using matrix and determinant. Okay. So having some fixed point, okay, in 3D space. So the first application which I have taken is, suppose if I am having two vectors A1 and A2 which are fixed point in the plane, and I need to find the equation of straight line which goes through these two vectors, right? Which are passing through these two vectors. I need to find an equation of straight line. So what will I do is, I know that the standard equation of line is simply ax plus by plus c equals 0, right? And since a1 and a2 are on the same line, I'll have two more equations which are satisfying the given equation 1. So ax1 by1c and ax2 by2c. These are the components of the next two lines, because considering an arbitrary point x comma y. So now I am having three equations, and as you can see, together these three equations will form a homogeneous system. Why they are forming a homogeneous system? Because A, B, C are the variables. They are not the fixed value. These are the variables. Okay. So if A, B, C are the variables, now see, we are having system of three equations, but they are having the same variable. The values are having the same variables, right? So what do we have from this point? That the determinant of x1 and x1 will be 0. Why it is 0? Because if A, B, C are the variables, then all these three equations hold the same variable, and if I take the multiplicity, then again I'll have infinitely many solutions. And if a system is having infinitely many solutions, then its determinant is always 0, right? Now, if minus fixed points on the plane, then the equation of line passing through these 2 points will be, just replace the value of x1 y1 and x2 y2. Its determinant is always 0 because they are having the same variables a, b, c. Okay, and when we solve this determinant, what we have is x plus y minus 1 is the equation of straight line. Now this is my straight line. This is my straight line passing through the point A1 and A2. Isn't it impressive part that how we can use the determinant in finding such type of equation? Okay, not only that part. If a plane, now we know that what is the equation of plane? It is ax plus by plus cz plus d equals 0. This is the standard equation of plane. Three lines, it is passing through 3 points. So this will be my equation 1 and rest of 3 equations. And again the same condition. The determinant of excluding the variables a, b, c and d. I'll have, and for the fourth column I'll have 1. I can have a standard equation of plane. Okay, passing this point and passing that point. So this is one of the best example of geometrical interpretation for determinant and matrix. And one of the example, let us consider one more example of circle. Suppose we have been given a circle lying in a space and there are 3 points x1 y1, x2 y2 and x3 y3 are on the boundary of this circle. But keep in mind that they are not in the same boundary of this circle. We don't know what is the center, we don't know what is the radius. Because if we know the center and radius, easily we can find the equation of circle. By the standard formula, we know that x minus h whole square plus y minus k whole square equals to r square, right? But as soon as we convert it into the standard equation of the circle, okay, what we know is that x square plus y square plus some what equation I will have the standard equation twice of bx plus twice of cx plus some d equals to 0. Now I have taken this 2 already. Okay, but if we don't know the center and the radius, we don't know the center and the radius, so we'll consider any arbitrary point on this boundary. Let's say it is x comma y. Let's say it is circle. I can say this is my standard equation of the circle, where I have chosen a to be the coefficient of x square and y square. The coefficient is always 1 for standard. Remember, it is for standard. But here, since we are finding a circle in the space, so we don't know coefficient of x to be b, coefficient of y to be c, and constant to be d. Now we have 4 unknowns, and 3 points are known which are lying on the boundary of the circle. So we have to we form these four equations with with the coordinates x1 y1, with the coordinate x2 y2, and the coordinate x3 y3. And again, since these four equations will have infinitely many solutions. Why they will have infinitely many solutions? Because all these four equations have the same coefficients a, b, c, d, and they are the unknowns. So we'll take its determinant to be equals to 0. So if I have infinitely many solutions, then the determinant is directly becomes 0. Okay. Now, say these are my 3 points. 1, 0, minus 1, 2, and 3, 1, which are lying on the circle. Just I need to replace the value of x1, y1. Okay. So vector v1, vector v2, vector v3. So I need to replace the values of the vectors. Okay. And the moment we replace the values, and how we will replace the values? It's very simple. My vector v1 is based on 1, 0, right? And in the system of determinant, how we have used the first column? It is x square plus y square. Okay. Similarly, 2. So x square plus y square is nothing but 1 plus 4, which is 5. As you can see my third row, the first element. So the determinant of this, the moment I take 0 and if I simplify, this is my equation. But as we know, the standard equation cannot be defined like this. I'll divide it throughout by 6. So x square plus y square minus 14 by 6x minus 26 by 6y plus 8 by 6 equals to 0. Now, using that formula, that coefficient of x and y, half of the coefficient of x and y, okay, since they are negative, so the center will lie in the first quadrant, and this is the center. And finding the radius of the standard equation, I have to consider the value of r to be square root of the values defined in the center apart from this value d, using the formula of finding the radius. So this is my equation of circle, having the center 7 by 6 and 13 by 6 and radius 37 by 18, which we would like to calculate without the center, without the radius, but 3 points are known to us. Okay. So these are the geometrical interpretation of the, and this can also be used to calculate the orbit of planets using Kepler's first law. This is how we use, right? So these are some of the basic examples, and there are many more examples to go based on the application of this part. Linear, okay, linear algebra. So thank you, and your questions, your doubts. Thank you, ma'am. Thank you, ma'am. Thank you, and thank you. Yes, ma'am. So, if there are any questions from the participant side, okay, there is. So, if there are any questions related to topic with you, Okay, how the scale depending the clarity of the picture. See, it all depends on the moment we take a matrix, and we know in image processing, a matrix is not just a small matrix which we have studied 2 by 2 or 3 by 3 matrix. If we take a picture and its clarity is of high resolution, say 1080p, okay, then the matrix will be of n by n matrix, or it will be of order n by m matrix, where the value of n and m can be in lakhs. The values are not small. Okay, so we are taking the linear combination. Okay, we are taking the linear combination. So the resolution of the original first matrix we have taken as 1, and the second matrix we have taken as by half. We have reduced, what we say, we take the picture in blur mode. Okay, so if we combine these two pictures, then the resultant will be the picture as we have seen. Okay, I hope the idea is clear. The scalars depending on the clarity, because the scalars decide, they are scalars and we multiplying with the elements of the matrix of the image.
Uh, yeah, Thakran sir, I have a just one query that
Yeah.
uh, what is the main concept of this linear algebra? Although all world are behind this to use in artificial intelligence, AI and ML, and uh, how it can be more give some insight on this.
Okay, in machine learning, you're saying.
Yeah, yes, yeah.
Okay, see, machines doesn't know what we are saying. They know only the values, say 1 and 0. Okay, so whatever the feedback we give in machine learning, whatever the feedback we give in the commands in bit system, ones and zeros. Okay, and these ones and zeros, these bits and bytes can be arranged in the form of matrix, some set of commands, which are given by, it forms a vector space. How we want to frame our say statements, how we want to frame our sentences for machine learning. That all depends on how the vector space. One more basic part is linear transformation, so which I have skipped my lectures. So linear transformation is the part where we can give this the applications in the AI machine learning part. But basically, the values, the vectors, they always contains the values in the form of zeros and ones. They are not just some regular matrix. And even in image processing also, which I have taken the example, it's a part of AI/ML only, image processing, where the matrix containing the values ones and zeros. Okay.
Yes, we get to know that how it can be useful.
So
Then, if possible, can you open your this thing, camera?
hello. I think the point is clear to you, sir.
Yes, 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 yeah. It is clear. Thank you. Open your webcam if you want.
Actually, I have Actually, the moment I start my webcam, okay, I'll use my, okay, I think,
Yes. Thank you for your informative talk. And was really something for you, the basic concept. Thank you. From my side, so, like organizer
participants, and thank you to the organizers. Thank you, madam.